As a second example of propagation of uncertainty, I'm going to use the voltage divider. Now, a voltage divider is a circuit that's comprised of two resistors, and you're going to become very familiar with the voltage divider equation in this class. It's going to be something that we're going to use often as a simplification, starting to commit this to memory may come in handy in the future. The voltage divider equation looks something like this. All right, if we have an input voltage, that's our V sub I, and two resistors connected together, and we know the input voltage and we know the values of the two resistive elements, we can determine or calculate the output voltage. All right, and the output voltage is VI multiplied by the value of R2, this resistor right here, divided by the sum of R1 and R2, or the total resistance of the two combined elements. Okay, so now let's say that we have we want to calculate the expected voltage output with confidence, with 99% confidence, if we know that the input voltage is 12 volts plus or minus 0.02 volts. We know that we have a 1.4 kilo ohm resistor, or 1,400 ohm resistor with a 5% tolerance, and a 1 kilo ohm resistor with 5% tolerance. All right, what's the approach to doing this? Well, the first thing is let's write down all of the information that we have available. We know that the input voltage is given to be 12 plus or minus 0.02 volts. R1 is, again, 1,400 ohms plus or minus 5%. And R2 is 1,000 plus or minus 5%. Okay, so the next thing that I'm going to do is I'm going to use that information, and I need to, before I can do these calculations, I need to convert that relative uncertainty into an absolute uncertainty. So if I take 1,400 and multiply it by 5%, I get an uncertainty of 70 ohms. So this really is plus or minus 70 ohms here, and this is going to be plus or minus 50 ohms for R2. So once I have that information in hand, the next thing that I'm going to do is I'm going to have to start, I'm going to write down my voltage divider equation. My voltage divider equation is V out is equal to Vn times R2 over R2 plus, or sorry, R1 plus R2. Okay. Now that I have all of that information captured, what I'm going to do is I'm going to rearrange my voltage divider equation just a little bit to make it a little easier to take the partial derivatives. So what I'm going to do is rewrite this as Vi times R2 times the quantity of R1 plus R2 raised to the negative 1. All right, so that'll just make it a little bit easier to do the partial derivatives. Notice that since we have this plus term in here, we cannot simply apply the relative uncertainty formula where we take delta V over V, delta R1 over R1, and delta R2 over R2. We cannot do that because we have this additive term in here. Okay, so we have to do the partial derivative term to get the correct propagation of uncertainty here. All right, so what I need to do is I need to take the partial derivative of my output voltage with respect to each of the measured variables. So I'm going to take the partial derivative with respect to Vn. Again, I'm going to pretend that Vn is my variable and everything else is just a constant. So if I take the input voltage variable and assume that that's the variable, everything else is constant, the derivative of a first order term goes to a 0th order term, so Vi raised to the 0th power, which would be 1, and my partial derivative would be R2 times the quantity of R1 plus R2 raised to the negative 1, which can be rewritten as R2 over R1 plus R2. Okay? I also need to take the partial derivative of the output voltage with respect to R1, because that has some uncertainty associated with it. It has that 70 ohms of uncertainty. All right, so again, I'm going to hold R1 constant, or sorry, R1 is my variable and everything else is held constant. Okay, so I have to remember my chain rule here. So first of all, I'm going to take the derivative of this entire expression because it has R1 in it. So I'm going to use my calculus tricks here, or my differentiation tricks. If I take the u substitution root here, this whole term right here is my u. I'm going to take the derivative of that will give me negative Vn times R2 times the quantity R1 plus R2 raised to the negative 2. Okay, and then I need to multiply that by the derivative of this u term, or whatever is inside this quantity right here. But the derivative of what's inside this quantity with respect to R1, the constant term is going to go away, and R1 is going to just end up being raised to the 0th power, which is 1. So we'd multiply, in essence, to be precise about that, we'd multiply by 1, which would essentially just give us negative Vn R2 over R1 plus R2 quantity squared. Okay. Finally, I'm going to take the partial derivative of the output voltage equation with respect to R2. All right, so here we're going to have a product rule that comes into effect. Oops, excuse me. Under here, we're going to have the product rule that comes into effect because we have both R2 here as well as here. Okay. All right. So let me progress. The first one, I'm going to assume that this term right here is going to be the variable. So I'll take the derivative of this term and multiply it by the two remaining terms. So that would be Vn R2 times the quantity R1 plus R2 raised to the negative 1. And now I have to take the derivative of this quantity and leave this one alone. All right, so that's going to give us negative Vn R2 times the quantity R1 plus R2 raised to the negative 1, to the negative 2. And then I have to use my u substitution here. I need to take the derivative of what's inside with respect to R1, but the derivative of what's inside with respect to R1 is just going to be 1. So this partial derivative winds up being, I'm going to pull the, this term should not be here because when I took that derivative, that term goes away. Vn times R2 raised to the 0th power, so that term goes away. I apologize for that. So now what I'm going to do is I'm going to pull out my input voltage terms, okay, and I will be left with 1 over R1 plus R2 minus R2 over R1 plus R2 quantity squared as being the partial derivative of the output voltage with respect to resistance R2. Alright, so if we go back to our voltage divider example here, we find that, look, I've already calculated those values out. So now what I'd like to do is show you a little trick that I use to keep track of all of this information. What I've done in this Excel spreadsheet here, and I'll blow it up to be a little bit larger, make sure we can see it all, is I have entered my nominal values for the input voltage, the resistor values, as well as the absolute uncertainties here. I applied a formula here. I multiplied my value by the 5% uncertainty in each of these to come up with the absolute uncertainty values. All right, I've computed how I will, I've calculated, derived the partial derivatives of the output voltage with respect to the input, the resistor 1 and resistor 2. Now I'm just going to plug in the values based on the formulas. So if I go back here, I see that the partial derivative of the output voltage with respect to the input is R2 divided by the quantity of R1 plus R2. Okay, so I can plug that in to determine the values. So again, it's R2 divided by the quantity of R1 plus R2. Okay, and I'm going to do that for all three of these. So for the partial derivative of the output voltage with respect to R1, I have the following equation. It's equals negative Vn times R2 divided by the quantity of R1 plus R2 squared. Okay, and that's the value that I get there. And then finally, I'm going to plug in the partial derivative that we calculated with respect to R2, and which is this nasty thing right here. So bear with me while I get that entered in. So that is Vn times the quantity of 1 divided by R1 plus R2 minus R2 divided by the quantity R1 plus R2 squared. And I think that should be it. There we go. So that's the value of the partial derivative. All right. Now, for each of these terms, what I need to do now is I need to take the partial derivative value and multiply it by the absolute uncertainty in the variable with which I took the partial derivative with respect to. So this will be the product of the partial and uncertainty. All right, you want to make sure that your partial derivatives here line up in the same order as the variables of the measurements that you took right here. So I'm going to take the partial derivative value and multiply that by the uncertainty in the input voltage. Okay. And for this one, since I took the partial derivative of the output voltage with respect to R1, I'm going to take the partial derivative value and multiply it by the uncertainty, the absolute uncertainty in R1, and I'll do the same thing here. I'll take the uncertainty value the partial derivative value and multiply it by the uncertainty in R2. Okay. Then what we need to do is we need to either take the absolute value or square those terms. All right. If we take the absolute value of those terms, we can add them all together. And this will give us our most likely uncertainty in the output voltage. Or sorry, not the most, excuse me. This will give us the maximum uncertainty at the 99% confidence level for the values given. Now, if we square all of these terms, I'm going to take the uncertainty terms, the product of the uncertainty terms, and square them. Okay, and then I'm going to sum them all up. And then I'm going to take the square root of that. Let me try that again. SQRT, there we go. All right. Then this is going to be the most likely uncertainty. So this term right here is the maximum expected uncertainty in the output voltage, and this is the most likely right here. Okay, I find that using Excel is a very handy way to keep track of all of the numbers after you've calculated the partial derivatives to make sure that you don't get confused and bogged down in tracking numbers down. Okay, so again, if we go back to our information here, we should see that that's what we got for the most likely uncertainty. All right, and again, note here that relative uncertainty analysis will not work in this case, right? Because we have this additive term here in the denominator of the voltage divider equation. Okay. Now that we've gone through that, we will do some practice in class with this, and I hope you have a better understanding now of how we actually perform the propagation of uncertainty analysis.